Okay, so today we will be talking about the division property of radicals, the mysterious third operation, you know? So this will be chapter 6.6. Let's just get into it. I'm going to strongly insist that you know the definition of a simplified form of a radical is, because we will be using it, probably, maybe. All right? So let's talk division. Remember earlier, or in the last video or whatever, I was like, oh, you know, like, the kth root of a is the same as saying, like, a to the 1 over k, right? And I know I mentioned this a couple times before already too, so now. And remember how I said that, like, oh, well, what? Oh, a over b is the same as saying a times b to the negative 1, right? And you know how I said, oh, well, a, b, the whole thing to the k is the same as a to the k, b to the k. You see where this is going, right? Well, if we squish all of this together, we actually get the property that the kth root of a over b is equal to the kth root of a over the kth root of b. And for grade scope purposes, I want you to show why. I just want you guys to know how to do this, but I'm going to show you guys how to do it as well. So if you're paying attention, great. All right, here's how I would prove this, okay? Step 1, we know the kth root of a over b is the same as the kth root of a times b to the negative 1, right? And this uses, let's call this property 1, 2, 3. This uses property 2. All right, step 2, I know that the kth root of a times b to the negative 1 is equal to a times b to the negative 1 to the 1 over k, right? And this uses property number 1. And then I know that a times b to the negative 1 to the power of 1 over k can be distributed using property number 3. So I know that this is a to the 1 over k times b to the negative 1 over k. All right? And now I'm going to have you guys do step 4. Oh, and this uses property 3. Step 4 uses the property of, like, p to the negative 1 is equal to 1 over p to the first, right? And step number 5 uses property 1 once again. Okay, so finish this off, send it up to Gradescope, all right? So that's the division property of radicals in a nutshell. Oh, important distinction, b can't equal 0 because you can't divide by 0. All right, that's the division property for you. The next thing we'll cover is rationalizing the denominator, okay? As you guys may remember, a rational is something that may be written as a proper fraction, so like 1 over 7, 3 over 8, stuff like that. Radicals are not always rational, so like root 2 is not a rational number, right? So when we want to rationalize the denominator, we want to turn the denominator into a rational number. For our purposes, we want it to be an integer, okay? We don't want weird fractions. Or, to be very specific, we want the denominator to be either an honest-to-God value or an honest-to-God variable. We don't want root whomevers, okay? Okay, now, this is very important. My first question for you, you don't have to show this to Gradescope, is question number 1. Is 3/5 squared equal to 3/5? Do it out and come back. Because based off of this, I'm going to ask you a follow-up question. The follow-up is 3/5 equal to 15 over 25? Okay, the answer for your first piece should be absolutely not. 9/25 is not equal to 3/5. That's silly, right? The answer for your second piece should be absolutely, right? Because 15 can be written as 3 over 5. 25 is 5 times 5. 5 over 5 is equal to 1, right? You have a ratio of 1. So that leaves you with 3/5 times 1, which is equal to 3/5. All right? This is very important because when you rationalize the denominator, you can't just square things and make your problems go away. That's not how that works, right? As we established here, squaring it does not maintain the ratio anymore. What does maintain the ratio is multiplying the top and bottom by the same value, because that's just the same as multiplying by 1. Yeah? So, when we rationalize the denominator, what we're doing is we're multiplying by some value, on top and bottom, such that the denominator has no radicals and the ratio value is preserved. Okay? For example, a ratio of one teacher to 10 students is preserved when you have 2 teachers to 20 students, right? But if you square it, 1 teacher to 10 students is not the same as 1 teacher to 100 students. That's called breaking the law, okay? So, don't break the law. Now that we have the ground rules, let's kind of, put it all together. Let's say, for example, you have 1 over root 3. That's not a rational number, or at least the denominator is not rational. How do you turn root 3 rational? Well, root 3 means that you have to multiply 2 of them together to get 30. Okay. So let's multiply by root 3 over root 3. Remember what I said about not squaring it. Okay then. And then that leaves us with, we should know how to work with fractions today. Root 3 over 3. And you're done. Okay. Let's do a slightly harder one. Let's say I have root 7 over root 5. Which one is the offending number? It's not root 7, it's root 5. We're rationalizing the denominator. Okay, we'll multiply by root 5 on top and bottom. Not a problem, right? We know how to multiply rationals. This gives us root 35 over 5. All done, no problem. Let's do something an eensy bit harder. 10 over the third root of 2. Okay. The cube root of 2 means what? It means you need to multiply by 3 root 2 3 times to get 2, right? So here's what you're going to want to do, all right? You're going to want to multiply. There are 2 ways to do this, okay? Or 2 ways to represent this. You can either write it like this, again, top and bottom. Should have done it in green, but that's okay. Or you can write to represent it like 10 over oops, 10 over 2 to the 1/3, come on, 1/3 times 2 to the 2/3, right? It's the same thing. My personal recommendation is to do it like this because the fractions make sense. You want to get some number or some exponent, sorry, some variable to the first. The point is, you want to get the denominator to a legit, nice to work with number. 8 to the 7th is cool. 8 to the 3/5, You see? Either way, right, this should result in, well, the numerator does what the numerator does. It's going to be 10 times 3 root 2 squared. The square can either live inside or outside. Please don't put the square here. Both are fine. All over, well, the cube root of 2 times the cube root of 2 times the cube root of 2 is 2. Just like that. And then from here, we're like, oh, actually, this simplifies. And so you end up with 3 root 2 squared. Well, the square can live here. That's fine, too. If you do it the orange method, then you end up with, well, you end up with the same thing. You end up with 10 times 2 to the 2/3 all over 2 to the 3/3. 2 to the 3/3 is 2 to the first. 2 to the first is 2. 10 times 2 to the 2/3. Please don't try to cancel this stuff out with the bottom. We just added it back. We just put it back in. Don't get rid of it. All over 2. Oh, looky here. And that gives you 5 times 2 to the 2/3. Both are fine. Okay? Now, I'm going to give you a slightly harder one. What if I gave you, and I want this on Gradescope, what if I give you, I'll give you a cute numerator. Let's do 5. Okay, 5 is fun. 5 all over the 7th root of 3 to the 6th. My personal advice for you is don't tell me what 3 to the 6th is equal to, because you're going to have to take the 7th root of it anyway, and that's going to suck. Okay? My personal advice, turn this into a rational exponent, and then figure out what you need to multiply by to turn that rational exponent into a 1. Okay? So, that's it. That's how you rationalize the denominator with one term. And of course you can do this variables and whatever else makes you happy or unhappy. Okay. I'll show you guys one more alternative method for rationalizing the denominator. There's a couple different ways to look at it, right? For single terms, you can have, for example, 1 over, I'm going to use 1 so it's a bit more efficient. Suppose you had like 1 over the 5th root of 2 cubed, right? In principle, you don't actually even have to turn this into a fraction. You can just treat this as like a number. This is just 8, right? So in principle, you could, instead of saying this is the same as saying 1 over 2 to the 3/5, and then we want to multiply by 2 to the 2/5 over 2 to the 2/5, right? Which gives you 2 2/5 all over 2 to the 5/5, which is 2 to the 2/5 over 2. Totally could do that. Instead of doing that, you could just say, oh, well, I mean, 2 to the 3rd is just some number. Fine. You can just say, oh, this is the same as saying 1 over, over root 5, 2 to the 3rd, which is the same as saying 1 over 2 to the 3rd to the 1/5. Totally could. Times, to get this to a whole number, you just multiply by 4. There's 4 of them, right? You can just say 2 to the 3rd to the 4/5. Totally valid. To the 3rd to the 4/5, right? And that gives you 2 to the, we have to multiply these together, 12/5 all over, let's see, this and this gives me 2 to the 3rd to the 5/5, right? Which is the same as saying, oh, well, this is 2 to the 12/5 all over 2 to the 3rd to the 1, right? This method it's fine. It's just more simplification, in my opinion. 2 to the 12/5 all over 2 to the 3rd. Now we have to simplify, right? Now it becomes, I'm going to separate these as 2 to the 10/5 times 2 to the 2/5 all over 2 squared times 2 to the 1st. Hear me out. Because this is the same saying 2 squared times 2 to the 2/5 all over 2 squared times 2 to the 1st. These two cancel out into 1. That gives you 2 to the 2/5 over 2. And it's the same result. It's fine. It's whatever you're more comfortable with. Again, I personally recommend this, but if you prefer manipulating fractions in a more hands-on kind of way, that's fine too. All right, what we're going to cover next is doing rational denominators on, or rationalizing denominators on two terms. Okay, so two terms will look something like, ready? I'll give you the form first, and then we can kind of figure it out from there. Okay, so when we talk rationalizing denominators with two terms, okay, there's a very important thing. If you notice, these ones, they can be any root you want, more or less. With two terms, I'm going to restrict it to it being root 2, okay? I'll explain why in a second. So it's going to look a little bit like this, P over A plus B, right? P, pick an expression, any expression. Let's not be 0, because, you know, it's 0 over whoever, then it's 0, who cares, right? So P cannot equal 0, or else you get 0 or whatever, and A plus B cannot equal 0, because then that's undefined. Yeah, I think that's fair. Okay. Now, your third restriction is A or B, and this is not an exclusive or, okay? This is an inclusive or, all right? So it can be A and B. A or B must be a radical with index 2, okay? Okay. Ready? It's very easy. To rationalize this, you're going to hear me out. All you got to do is the following. Do you guys remember when I taught you guys how to factor and I said it'd be really important? Yeah, this is one of those times where it's very important, okay? If we go back to rationalize, or going back to factoring, right? If you have a plus b squared, you have a squared plus 2ab plus b squared, right? Which means that if we multiply a plus b by itself, and then of course you also have to do on top, like with the one-term situation, right? If you multiply by a plus b, you end up with a 2ab term in the middle. And what did we say? We said either a or b, or both, has to be a radical. A squared, suppose that's the radical one, you square it, index 2 squared is just the inside. Cool. What about the b term? B squared is radical, base 2, then it's just b. But that middle bit, right, it doesn't cancel out, it doesn't go away. And so you end up with some nice stuff plus weird radical behavior plus some nice stuff. We don't want that. Let's do a quick example. You have like 1 over 3 plus root 2. You multiply it by 3 plus root 2 on top and 3 plus root 2 on the bottom. you end up with 3 plus root 2 on top. That's no problem. And then you end up with 9 plus 6 root 2 plus 4. And you've done absolutely nothing interesting here. You see? So we don't want that. The second option is right, and of course this also applies to if b is negative, then you end up with a minus b, which is just a squared minus 2ab plus b squared. Again, you have that bad term in the middle. That's no fun, okay? The alternative is you multiply by its opposite, loosely speaking, right? And what I mean by that is you say, oh, well, a plus b, at least one of them has to be radical base 2, right? A minus b, right? You multiply these together and you get a squared minus b squared. There's none of that middle term. If a is the radical, it gets squared. Squared goes away. If b is the radical, it gets squared. It goes away. You have no problem. This is fantastic. And you're done, right? And the execution for this will look a little bit, on the same problem, will look a little bit like this. So 1 over 3 plus root 2. Your b is positive root 2. So you want to multiply by 3 minus root 2, right? Doesn't matter what your b is, as long as you switch the sign, you're probably good to go, all right? So you multiply by 3 minus root 2 over 3 minus root 2, right? On top and bottom, because that keeps the ratios the same. And that leaves you with 3 minus root 2 on top, nothing crazy here, all over, oh, what did we say? It was a squared minus b squared? Okay, what's a squared? 3 squared, that's 9. And what's b squared? Oh, root 2 squared is 2, minus 2. And all of a sudden, you're left with 3 minus root 2 all over 9 minus 2 is 7. Ooh. And that's it. Now I'm sure you're wondering, but Amanda, what if the denominator is not a root 2, it's a root 3? Why would I do that to you? Right? Why would I do that to you? But suppose you wanted to know. Suppose you wanted to know, right? Okay. If you confuse easily, ignore me. Fast forward. If you're nosy, lock in. Okay? So, let's do an easy example. This is where the sum and difference of cubes is really helpful, all right? So let's say, for example, you have, let's keep it at 1 on top, okay? Oops, there we go. 1 over 7 plus the cube root of 5. Okay. Okay. If you notice, this is a plus sign. It behaves a little differently than the 2 term with root 2, because with root 2, it doesn't matter if b is positive or negative, you just switch the sign on the b when you multiply for numerator and denominator. So like by that I mean like, oh, if this is positive, if this is positive, this is negative. And if this is negative, then this is positive. Yeah, right. That's fine. Cube roots, you can't do that because it's a cube root. I mean, I don't know what to tell you, right? So you have to be mindful of the sign, okay? I'm gonna rewrite that for you. 7 plus cube root 5. Okay. We know that this already kind of looks like the sum of cubes. It's not because it looks like this, like, oh, there's a plus sign. No. It looks like this, or it's not because it has a plus sign for the a cubed plus b cubed situation. No. It's the same because of the factor. Do you notice how the right-hand side is a plus b, That's what you want, okay? Because if you notice, this is that factor we're multiplying with, right? Or we're multiplying from, right? In the same way how this is the factor we're multiplying from our constraint, so we have to manipulate this. In that same exact way, this is our limiting factor, the thing that's giving us a hard time. So if you want to rationalize this, you're going to multiply it by, you have to figure out what your a's and b's are, okay? Your a is going to be positive 7, your b is going to be 3 root 5. It's going to get a little dicey, so be very careful. I will not quiz you on this, by the way. I'm not testing you on this, okay? I might put an extra credit problem, though, so, right? So, if you were to do this, you would say a squared, so it's going to be 7 squared. You could write it all the way out. You don't gotta. I'm not going to. Minus ab, so 7, 3 root 5, plus 3 root 5 squared. I'm going to choose to write the square on the inside, just because it's a little bit neater, like that, okay? Just like that. And whatever you do on the top, what do? Same on the bottom, very good. So it's going to be 7 squared minus 7, 3 root 5 plus 3 root 5 squared, just like that. Okay. Now, if this wasn't a 1, and it was like an 8 or an x or whatever, you could just leave it like that, in the sense of, once you write it out, you'd just be like, oh, it's going to be like 1 times, right? I'm not going to make you do it out, okay? Because this problem is hard enough the way it is. This leaves you with 7 squared minus 7 is 3, 5 plus root 3, 5 squared. Close. All over what? Remember, we're multiplying across, right? Well, the bottom right here should look just like that. That. Yeah? It should give you a cubed plus b cubed. What's a cubed? 7 cubed. I don't care what that is. Do you? No, of course you don't. 7 cubed plus root 3, 5 cubed. I'm going to write the cube on the inside. The cube root of 5 cubed is 5. Very good. And so your final answer should look a little bit like 7 squared minus 7, 3, 5 plus 3 root 5 squared, close, over. 7 cubed is 49 times 7, it's 280 plus 63, what, 343? Something like that, doesn't matter. 7 cubed plus 5. And just like that, magic. And what if you have a difference of cubes? What if it's like, oh, it's subtraction? That's fine. Let's do a slightly nicer one so we don't have to write as much. Let's do it 2 over the 5 minus, actually let me change this 2. Let's call this 7 and then the cube root of 2. Again, what factor are we working with? We're working with a negative factor, so we want the difference of cubes, yeah? So we're going to add. So, or we're going to use the additive one. All right, so we're going to multiply the top by a squared. A is 5, so 5 squared plus ab, so 5, 3, third root of 2 plus b squared. So it's going to be the cube root of 2 squared. Just leave it like that. There's no need to do it out. At least for this problem. You're doing the same on the bottom. 5 squared plus 5 third root of 2 plus third root of 2 squared. Just like that. And what is it again? Oh, right. If we multiply this and this, it's just the difference of cubes. Okay. Excuse me. Which should give you a cubed minus b cubed. So, our numerator, we multiply all the way across. It'll be 7 times this abomination. 5 squared, 5 third root of 2 plus third root of 2 squared. You can write that as 4 if you want. All over what? All over a cubed minus b cubed. What is a cubed? 5 cubed. 125. Minus b cubed. 3 root 2, which is what? 3 root 2 cubed is 2. If you really want, you could write it out as, because because the bottom is pretty easy to do for this one, but you don't have to. All over 125 minus 2 is 1, 2, 3. Ta-da! And that's how you do it. Now, of course, right, you're like, but Amanda, what if the inside of the radical is bad? That's fine. That's okay. Just use the index. So, like, if you're working with 1 over, 1 plus the third root of 7 squared, forget the 7 squared. You don't have to do any magic with that. You don't have to, transform it like we did over here, where you do some fun fraction magic. No. Over here, no. Don't do that. Here's what you're going to do. You're going to say, oh, this is going to be 1 over, or this is going to be multiplied by, okay, well, this is additive, so we're going to want the subtractive, so it's going to be 1 squared minus 3, the third root of 7 squared, plus the third root of 7 squared, which is 7 to the 4th. Don't do it out, it's fine, leave it alone. If you really want to do it out, it should be 7 root 7, 7 cube root 7, but you don't have to do that. All over what? The same thing, 1 squared minus 3, 7 squared plus 3, 7 to the 4th. And if you do it out, the numerator stays the same because we're multiplying by 1 in this case, so it'll give you 1 squared minus 3, 7 squared plus 3, 7 to the 4th, all over what? Oh, yeah, we're using the subtractive, the subtractive. So that'll be a cubed plus b cubed. A cubed is 1. B cubed is the cube root of 7 squared cubed. Oh, look, and that's just going to be 1 minus cube root of 7 squared plus the cube root of 7 to the 4th, all over 1 plus 7 squared. Ta-da! And that is it for rationalizing all sorts of weird denominators. Now I have to edit this.